All right, this video is going to be an overview of the first parts of chapters 15 and 16. So chapter 15 is about non-renewable energy sources, but the first part looks at just kind of energy in general. So the core case study is a really good introduction to human energy use over time. And again, just like when we were talking about human population growth, the Industrial Revolution plays a key role here, just like it did with the demographic transition. That's where we see huge increases in the amount of energy use. So in the 1800s, the primary energy source was wood, and that led to a lot of deforestation here in our part of the United States. That's why we don't have old growth forests. It's all new growth because most of the trees were cut down. In the mid-1800s, with the discovery of coal and petroleum, those became more useful. And in 1900, 40% of energy was from oil. The 1950s, that's when nuclear power was first introduced. I do have some updated statistics here for the world and U.S. energy use. So in 2015, which is the most recent thing I could find from a reliable source online, 2015, 32% of the world's energy use came from oil, which is a decrease of 2%. Coal was up 4% to 28%. Natural gas was also up to 22%. Nuclear was down, only 5% of world energy use comes from nuclear power. And then renewables make up a total of 14%, which is actually an overall decrease based on the data presented in the textbook. And of that renewable, most of it comes from biomass. 10% of energy use was from biomass, and then followed by hydro, and then other uses. In the United States in 2016, from the EIA, petroleum and oil use was at 37%, which is a decrease of 3%. Natural gas went up 6% to 29%, and we'll talk about why that is later on. And coal use decreased by about 7% to 15%. So that was a really significant change. So I think those three changes there with natural gas and coal, and then renewable, which we'll get to in a second, are significant to remember. Nuclear went up slightly to 9%, but that can be changing, as we'll see. And then renewables were at 10%, so that was an increase. Biomass, not nearly as much as in the worldwide data, but 4.6%. Then hydro, and then geosolar and wind. Wind had a huge increase there. All right, so 15.1, what is net energy? Why is it important? So net energy is the total amount of useful energy minus the energy needed to make it available. So if you think about the laws of thermodynamics, that comes into play here. So we have some net energy ratios of some different energy sources for in figure 15.3 for space heating, industrial heat, transportation. Some of these numbers might be a little bit different now based on different technology just in the time since this textbook was written, but it gives you an idea. What you have to remember with net energy is the higher the number, the more net energy. If it's 1, the net energy ratio is 1, that means get the same energy in as you do out. And if it's less than 1, you have a net energy loss. So that would not be a good thing. So subsidies, which have come up a few times earlier this year. So subsidy is money from the government or taxpayers that helps a business or an industry keep the cost of a service or good low and competitive. So anything that has a really low net energy to actually financially work will probably be subsidized. So nuclear is a good example of a heavily subsidized energy source. All right, so we waste a lot of energy. 84% of commercial energy use is wasted. Okay, about half of that, 41%, is due to the second law of thermodynamics. So when you change from one energy source to another one, some of it gets lost as heat, right? It becomes a lower energy. But then the other 43% is due to inefficiency. So that's what we're going to be looking at when we look at the beginning of chapter 16, which is what we're going to now. All right. So chapter 16 deals with energy efficiency, which is what we're going to look at now, and then renewable energy. So the core case study here focuses on passive solar design and energy efficiency. So kind of interesting to read, get some ideas of what can be done. All right, so energy efficiency. So we're back to that 84% of energy is wasted. And then we have some different solutions for why we should reduce energy waste. And we'll look at figure 16.2 shows this inputs and outputs, and we'll look at our own inputs and outputs. I've updated for 2016 data in class. So we have solutions, right? We're going to do a lot of things like prolong our non-renewable energy source, reduce pollution, local jobs, etc. So all good things. All right, so 16.2 is where we really get into how we can cut energy waste, looking at some actual solutions. Maybe we can actually see all the Post-its. All right, so one example that's being used in some places already is cogeneration. So this is the idea that when you are using a source of fuel to create electricity, basically what happens is you burn a fuel with most electricity generations. You burn a fuel that heats water, creates steam. The steam then spins a turbine, which is connected to a generator, and then that produces the electricity. But you could also use that steam, which contains a lot of heat, to then provide heat to a building. So there are some places that are doing this already. So that's pretty cool. Other solutions, variable speed motors that can only provide as much energy that it's use as much energy as necessary. Recycling helps to cut energy waste. The textbook talks a lot about compact fluorescent light bulbs, or CFLs, which I think just in recent years have been much more replaced by LEDs, and then a smart grid and smart meters. So these are all things that industry and utilities can do. Note about LEDs, kind of a local problem as we get into winter here too. So LEDs, because they're so much more efficient than traditional incandescent lights, they don't heat up as much. So one problem that they're experiencing now is traffic lights. It used to be that the snow would melt right off of a traffic light because they heated up. But with the new LED lights, they don't do that as much. And so that's become an issue that some cities and towns are dealing with. There are terms, there's a case study here about the smart grid. So there are kind of plans to modernize to a smart grid here in the United States, but it's still really in the early stages. There are exploratory committees set up, but nothing concrete happening nationwide yet. Another area where we can really help with efficiency is in transportation. So there are these corporate average fuel economy, or CAFE standards, which were started in the 1970s during the Arab oil embargo. And if you ask maybe if your parents or grandparents, aunts, uncles were around during this time, they might be able to tell you a little bit about like the lines at the gas station. But as you can see in figure 16.5, fuel efficiency has increased greatly during the early period, but then it's kind of petered off. And if you compare the US fuel economy to Europe, Japan, even Canada, which, our neighbor to the north, we're pretty bad. Right now it's currently split between, so overall the automakers have a average they have to get to, but split between passenger cars, which for 2016 they're supposed to be an average of 39 miles per gallon, and then trucks, so that will include like SUVs, etc., at 30 miles per gallon. Overall, the auto industry has been mostly successful in meeting these requirements, which is a great thing. But there's still some pushback, and there's a long way to go here. Some other ways to reduce transportation and energy use beyond just the vehicles is actually encouraging mass transit and high-speed rail lines with electric trains. In Boston, they're piloting right now dedicated bus lanes to make bus travel more efficient, encouraging biking. So a lot of places are doing, dedicated bike lanes, bike sharing programs. These are all things that, if we have less solo travelers, that will help. In terms of energy efficient vehicles, again, this is where we can see, even though our textbook's only like 7 years old, it's kind of dated. So you have information on hybrid cars, which are still more cost efficient than some of the other alternatives. So a hybrid car works with an internal combustion engine, which is how a standard vehicle runs with the gasoline. And then also it has an electric motor of the battery backup. And then plug-in models have all of that, but usually a smaller motor, larger battery, because they can store electricity and run further just on electricity. Hybrid car purchasing peaked in 2013. It was 3.1% of car sales, so still a pretty small fraction. This year it's down to about 2%, and probably the main reason for that is gas is a lot cheaper than it was in 2013. Then there are electric cars. The book talks a little bit about electric cars, but what you should know is that they've become much more affordable and dependable in the past couple of years. And, you know, it's not just like Tesla now, but Nissan and other companies are making electric cars that are more mid-range price, and they're getting so you can go travel further with on one charge. So we could see more electric cars in the future as well. And then you can get into the whole idea of like self-driving cars and how those could maybe drive more efficiently than people. Another area where we can save energy or reduce our energy waste is with buildings. So with new buildings and new construction, you know, you can take advantage of passive solar design. So that's things like having the building primarily facing south so that you get more sunlight, but then also having overhangs, etc. There's a description of one building in the textbook, covered it up with my Post-it. But so in the summer months, the sun is blocked, but in the winter months when the sun is lower, you actually get more of that heat. Using natural lighting, green roofs. The Whole Fields in Linfield at Market Street has a green roof. Those can help to absorb heat energy in the summer or reflect heat energy in the summer, absorb heat energy in the winter. Super insulation, and then all the other great things, you know, like solar heating, photovoltaic panels, recycled wastewater, etc. So there are a lot of things that new construction you can do. But then there are even things that can happen with current buildings, you know. So one of the most important things is insulation and stopping leaks. So you can see in figure 16.9 down here at the bottom, it shows all the heat being lost from a building. Energy efficient windows. If you think none of you guys were in the old high school, but maybe you remember it from coming to an event at the school, it was all these single pane windows that were really horrible, and we would literally have ice on the inside by the courtyard in the wintertime. So not very efficient. So we're doing much better now in our new building. Energy efficient appliances, lighting, you know, all of these things can certainly help. And then page 407 right here, there are some great energy saving tips that you could use at home. So this is something that you could always share with your family too if you want to, you know, super impress them with your environmental science skills. You can show them how to save some money and be good for everything else. And then the last part of 16.2 just kind of deals with some of the things that governments can do to help to save energy. And so just kind of summarize some of them. You can reduce subsidies for non-renewable energy sources, perhaps provide subsidies or tax breaks for renewable or energy efficiency, and then true cost pricing for things where you take into account things like pollution and cleanup costs, etc. But those are things that may or may not fly, but there are some ideas. So that's kind of the beginning. The rest of chapter 15 looks at non-renewables. We'll focus on that, and then the rest of chapter 16 with renewables.